I don't really know anything about it, but I know a couple of people who can probably help you. Come on, let's go. Go, go.
Let's zoom in real quick to see what is happening in her shin. The pain that the athlete might be feeling while she's running might be contributed to something called the medial tibial stress syndrome, MTSS, or better known as shin splints. Shin splints, or MTSS, is a repetitive stress injury of the shin area where repetitive muscle contractions and tibial strain cause the body to heal improperly. It is a very common injury, and it's a common cause for the exertional like pain in athletes. And some of the symptoms you might have already seen in the video include tenderness, soreness, or pain along the inner side of the shin bone and mild swelling of the lower leg. So let's take a deeper look into why or what might be causing shin splints from a biomedical approach with some professional biomechanists. Hi, my name is B.
I'm Felix.
And I'm Andrea.
And we are the biomechanists that will be explaining the athlete's problem with her shin. Due to COVID reasons, we are unable to meet with the athlete herself to discuss one of the possible causes of her shin pains. In order to determine possible causes of MTSS, or better known as shin splints, we must examine the force of muscle and the internal loading forces that are applied to the posterior-medial tibial border. And to pinpoint the differences in forces, we will be comparing walking and running forces. The values of these forces will be the point of reference for analysis of possible causes of shin splints. I apologize. We need to find the internal load forces, and in order to understand that, internal loads are the internal applied force as a result of other external forces. And we study this because it helps us explain mechanisms of injuries, which in this case is the athlete's shin splints. And so let's begin with looking at the diagram that I have here with A, B, and C marked with the tibia, the force of muscle, and the ankle joint.
Just as a disclaimer, I would just like to say that there is not a known cause for shin splints, but this is one of the few guesses that experts have.
To begin with, we're going to start with a walking free body diagram. This is the athlete when she is walking. This is our free body diagram, and it's flipped sideways with a different orientation, but we'll talk about that more in depth later. What are our unknowns and knowns? Our knowns are the weight. The athlete's weight is 550 newtons. The normal force is 550 newtons. The angle of the forced muscle is 20 degrees. The length of the tibia is 0.35 meters, and the thickness of the tibia is 0.015 meters. What are our unknowns? Our unknowns are the force of muscle, shear stress, V, and these are things we've never talked about before. So the shear stress is an underlying force that pushes one part of the body in a specific direction and another part in the opposite. This will typically be pointing downwards. The axial force, noted as NB, is a compressive or a tension force acting inside of a member. This is typically pointing out of the member. Then we have the bending moment, M, which is a moment which causes the element to bend. This can either point clockwise or counterclockwise. Okay, so this is our free body diagram again, and now we've placed all of our known values, and this is our orientation right here, X going up in a positive direction, Y going left in a positive direction, then we have our counterclockwise is a positive direction. And we're gonna start off by doing the equations of equilibrium. We're going to be starting with the sum of moments because this is the way we will figure out our force muscle. We do this at point C because this will cancel out several of our things like FCX and FCY and F normal. And once we do that, we set the force, the sum of moments in the C direction equal to 0. This is because this is a static equation. We're looking at a frozen member at a certain point in time. And our first thing is negative W because it's going in the clockwise direction with 0.015 divided by 2 because that's half of the tibia width. And then we have minus Fm cosine theta because that's going in the clockwise direction, and that's times 0.015 because that's like the width of the tibia minus Fm sine theta, which this is going in the clockwise direction too, with 0.35 being the length of the tibia. And then we solve for Fm. We would move the W to the left and then pull out the Fm, and then we would divide everything on the right to the left. And that's how we get Fm is equal to negative 30.829 newtons, which is the compressive force.
Awesome. Thank you, Felix. So now we will be looking into the internal loading forces within the shin. So for this, we have to split the shin into two pieces. So we will be focusing mostly on the A and B portion, but either way could work. So as you can see on the diagram, we've listed the axial force, the shear stress, and the bending moment. So again, as a point of reference, our axes are written down just to keep in mind. And next we'll be focusing on the sum of forces in the x direction. So once we solve for the forces in the x direction, we get negative v plus Fm sine theta. We are going to solve for v, and then with this, plugging in the values that we already know, we get that v is equal to negative 10.544 newtons. Next, we will be solving the sum of the forces in the y direction, which again will equal 0. This will be equal to the negative axial force and the negative force of muscle with the cosine theta. We will solve for the axial force and get the number to be negative 521.030 newtons. This will be a compressive force. Next, we'll be solving for the moments in the around point A, which will again equal 0. So again, the force of the muscle with cosine theta will be multiplied by 0.015 because this is the width of the tibia, and this was going in the counterclockwise direction. This is also subtracted by the weight times 0.075, which is half of the width of the tibia. This is going in the clockwise direction. Next, we subtract by the clockwise direction of the axial force minus the shear force, which is also going in the clockwise direction, plus the bending moment, which is going in a counterclockwise direction, sorry. And once we solve for the bending moment, we get it to be negative 1.193 newton meters.
Now we're going to go and study the athlete when she is running. We are using the same free body diagram as before. Now, what are our knowns and what are our unknowns? Our knowns is that the athlete's weight is 1,650 newtons. This is 3 times of what it was before because when you run, you put three more times the weight on your body. The normal force is 1,650 newtons. The angle now is increased 30 degrees because we have an increase of an angle when we're running in the muscle. And the length of the tibia is 0.35 meters, and the thickness of the tibia is 0.015 meters still. And what are our unknowns? Our unknowns are still the same: force of muscle, shear stress, axial force, and the bending moment force. Now we're going to use the same free body diagram as before with the same orientation. There's just a few changes in the values, such as the theta being 30 now and the weight being 3 times what it was before. So now we're going to set up the same equation, just different values, and we're going to get that Fm is negative 65.828 newtons, and this is a compressive force.
So again, for the running portion, we'll be looking into the internal loading forces. And by doing this, we'll be doing the sum of the forces in the x direction, which is the same as we have done previously. And we find that V is equal to negative 33.914 newtons. Then we do the sum of the forces in the y direction, which is again similar to the one we did previously, just a changing in the weight and angle. So once we plug in the known numbers, we get that the axial force is negative 1,592.991 newtons, which again is a compressive force. Then we do the sum of moments in the around point A, which is equal to 0. Again, this is very similar to the one we already solved for before. We're just plugging in different values this time. This solves for the bending moment to be negative 4.477 newton meters.
Now, this is a summary of all our findings of our unknowns. First, we have the values for walking, and then we have the values for running. As you can see, all the values increased. Specifically, the force of muscle increased by 2 times.
And what does that mean in terms of shin splints?
That just means when you're running, you have a repetitive contact to the ground, and the force of muscle has a 2 times increase in force, and that just causes pain to the bone, which is felt in the tibia and shin splints.
Next, we can see that the shear stress and axial force increased by 3 times. Next, the bending moment also increased by 4 times.
So what do these internal loading forces mean?
Right, so the internal forces, for example, the shear stress leads to a deformation of the bone, but since it only increased by 3 times, it isn't such a huge concern, and since it's a repetitive motion, it's not like the bone is constantly being deformed. For the axial force, this is a compressive force, so this force can actually lead to buckling, which if the force were great enough, it could lead to the eventual shattering of the bone. But for the most part, the one we want to focus on is the bending moment, since this had a 4 times increase. This causes the bone to bend more, which can cause micro tears and micro fractures within the bone, which is overall what we feel in shin splints.
Now,
Thank
what do we recommend for the athlete? So these are some recommendations we are giving to the athlete. Um, First, we recommend a cushioned running shoes, which would help with an increased support on the lower leg and soften the force of the lower leg on the ground and would create less force on the leg. And we also recommend a shin brace, which would increase the sturdiness of the shin and decrease the amount of force within the tibia.
All right, thank you guys for tuning in and happy pain-free running.
Bye.
Bye.
Thank you.